In the last class, we had discussed that sorry, if you have a if you want to compute the normal cone of a convex set given by convex inequality constraints, then if you have the Slater condition, the normal cone is a polyhedral cone generated by the gradient of the active indices, right? So that's what we had learned. But you see, if you want to make, you might be uncomfortable with always writing the gradient of the active index set, knowing that from point to point the active index set would change. You might want to make a much more easier writing. So if you say that, okay, at any given point, uh, any given point x bar, look at those gi x bar which is strictly less than 0. With them, associate the lambda I equal to 0. Then you can simply write, putting those lambda is equal to 0 and bringing into the sum those gradients of those inactive constants, that is I not element of I x bar, that is gi x bar is strictly less than 0, and have any vector v in Sx bar written like this, which where I is not just on Ix but it ranges from 1 to m, but we'll have this additional condition which we call the complementary slackness condition. A similar type of thing came in the computing the normal cone of Rn plus. I'm sure you remember, it was in the last class, last to last class. So last to last lecture, I would say, not really class. Class is very difficult to define here on online stuff. So now this condition is very, very important in optimization. It comes out, it tells, finally it will tell you that associated with every minimization problem is a maximization problem, but we will not go into those details. But economists would finally would need such details, because in economics both type of problems can come in. So this is called the complementary slackness condition, means both of lambda i's and gi's cannot simultaneously hold with strict inequality at the same time. That is, if gix is strictly greater than 0, strictly less than 0, you cannot have lambda I strictly greater than 0. Lambda I must be equal to 0. That's what it means. That is exactly what we did, setting lambda equal to 0 when gi x bar is strictly less than 0. So that whole thing can be combined into this small thing, small condition. Okay. Now we are going to do a very important result here. This result will actually allow us to finally write the Karush-Kuntakar condition or KKT condition, which you will soon come to know, in a much more representative and easier form. Okay. Now, see, we have computed f1, the normal cone to f1 at x bar. We have not computed normal cone to f1, a normal cone to the intersection of f1 intersection x. Normal cone to at x bar to the intersection of the sets f1 and x. So n of x bar at n of f1 intersection x at x bar, that cone we have not computed yet. But that cone we do not need to compute. Actually, the Slater condition will give us this thing. Now, here we will consider in this lemma, an important one here is, you see, the whole idea is to construct the normal cone and then finally use it for optimality condition, because that is how you keep our logical flow. If any other path I would have taken, it would be illogical. So what we have done here is to note that we will assume that, consider the set f1 intersection x and assume the Slater condition holds true. In this case, the Slater condition, I would not say really Slater condition, I would say modified Slater condition. We mean a slightly modified version of it, which means I will need a point x hat element of x such that gi x hat is strictly less than 0. That is what I will require. I will require the x hat where this Slater condition is holding, it must be an element of x, capital X, which says that if you take x bar element of f1 intersection x, and if there exist scalars lambda I belonging to the active index set, and lambda I greater than 0, such that whenever the negative of lambda I grad gi x bar, that is negative of the any vector belonging to Sx bar, which is n f1 x bar, because the Slater condition is holding, if that belongs to nx bar, then that vector from Sx bar must be 0 actually, that all the lambda i's would actually become 0. That is what the result says. Proving is very, very simple. It simply says that you assume, again I'll tell you, we keep on doing the same thing over and over again, the proof by contradiction methodology. This is possibly one of the greatest, this reductio ad absurdum is one of the greatest tool in the hands of the mathematician. So let us assume that our conclusion is not true. So what would happen? So there must be a mu I where I is running over Ix bar and all the mu i's are not 0 such that this linear combination of grad gi x over I element of Ix bar, positive linear combination, the negative of that is in element of nxx bar. So there exists a non-zero element of the normal cone to f1 at x bar, the negative of the, and such that the negative of that vector is element of nxx bar. Okay, now let us take the convexity of gi and let us choose that x hat, that point where you have the Slater condition. X hat is both belonging to f1 and x, right? So so GI, so you apply the convexity criteria and you know that GI x bar is equal to 0, so you will have this. Now you know also that GI x hat is strictly less than 0, whatever, because for all I, so for all I element of I x bar is also true. Now this simply says that if I now multiply by mu I, one of the mu i's are non-zero. So this now this is strictly less than 0, so none of these grad GIX can be 0. Right, x hat and x bar are not the same point because x bar has indices where gi x bar equal to 0. Here everything is strictly less than 0 for x hat. So these are different points. Now if, because of this, for every I, this is strictly less than 0, grad none of the cases grad gi x bar would be 0, or else this will become 0, it will be a contradiction. So which means that if I multiply by mu I, because one of the mu i's is positive, this inequality will be maintained and this whole sum would be strictly less than 0, which would be minus of this mu I gi x bar x hat minus x bar would be strictly greater than 0. What would mean? It would mean that minus of this, so minus of the mu I grad gi x bar is not an element of nx x bar. This contradicts this f, not e, it contradicts f. Sorry, this mistake, it contradicts f. Hence, mu I must be equal to 0, right? So it's a simple proof. Now let us come to our result, theorem 8, the main result of this chapter. This is actually the Karush-Kuntaker condition written in a slightly modified form because we have taken an abstract condition. So let us just read the result, try to understand the result. Then we will talk about the proof. So understanding the result at this moment is more important than understanding the proof right away. So we will consider the problem CP1, the simple one. We will not get into the other issues. Now let us consider the problem CP1. Let x bar be a global minimizer of CP1. Let there exist x hat element of x bar such that gi x hat is strictly less than 0 for all I element of all I ranging from 1 to m, which means that the Slater condition or the modified Slater condition holds. Then I would be able to find the lambda element of Rm plus, that is a vector lambda with whose all components are greater than equal to 0, such that 0 is contained in the sum of the vectors grad fx bar plus the sum of the positive or non-negative linear combination of lambda I into grad gi x bar. Here the grad is missing. Without the grad it won't happen. You will see the next part, you will see the grad coming in here, so that there will be a grad here. So while writing my pen you seem to slip a lot, which you don't when you are typing, but unfortunately there was no time to type, so I really beg your pardon. And so plus nx bar. So if you translate nx x bar by this amount, 0 must belong to that new set. and the complementary slackness condition holds. So let us see. So what does it say? Let us look at the situation if X is an open set. If X is an open set, this is nothing but 0. So this whole thing just becomes a vector. So it becomes 0 is equal to grad fx bar plus summation I equal to 1 to m lambda grad gi x bar. So when x is open set or x is Rn, then this combination actually becomes equal to 0. Or grad fx bar plus summation I equal to 1 to m lambda I grad gi x bar is equal to 0. So this is a very, very important thing. And you can immediately understand, suppose I forget this thing, there is no x or x is Rn, right? And this is nothing. These two conditions, these expressions actually come from the computation of the normal cone. So it will simply mean that 0 minus grad fx bar actually element of the normal cone. So normal cone is actually giving you these conditions where multipliers are involved. These lambda i's are often called the Lagrange multipliers, keeping in the traditional view of Lagrange multipliers, which you have learned in calculus, multivariable calculus, and this is called the KKT multipliers. Please understand, learning inequality constants is important. Inequality constants are hallmark of modern optimization because very important applications in engineering, in management, in finance, and economics all involves inequality constants and not just equality constants. So there's a lot of difference, right? So what happens? Let us try to prove it. Now, because the Slater condition holds by theorem 7, we learned this fact. But as x bar is a minimizer of CP1, then minus grad fx bar must be in the normal cone of F1 intersection at x bar. Now, if you look at lemma 1, which was this one, so each of these elements that you see, except the minus, is an element of Sx bar, which is n F1 x bar. And when you take a minus, it is in the cone minus n F1 of x bar. So what does it say? This lemma says that the intersection of minus of nf1 x bar with nx x bar is equal to 0. And when we that is exactly what lemma 1 says. So the qualification condition to apply the calculus rule for the normal cone is immediately there. So you know that n f1 intersection of x bar is the Minkowski sum of n f1 x bar plus nx of x bar. So what does it mean now? So from this result, now I am taking the grad f on the right hand side to write 0 belongs to grad f1 x bar plus nf1 x bar plus nx x bar. Basically, I am replacing this condition, this thing here, with this sum. Now I already know that nf1 x bar is sx bar. So 0 is element of grad f1 x bar plus sx bar plus nx x bar. So there exists lambda greater than 0 because I am now writing. So now there must be a specific element of sx bar and a specific element of w, so their sum must be equal to 0 because 0 is inside this particular set, right? These are all additions of set. These are singleton set and these are not singleton set. So because I do not know a specific structure of x, I keep quiet with it. But because I know the specific structure of Sx bar, I know that I can show that there must be some element of Sx bar such that added with the gradient of, why am I writing gradient of f1? Sorry, it's gradient of f. So that added with gradient of f would actually give me, so gradient of f would, so so there exists some element. So I cannot say all lambda is, so some lambda is that will generate this element where I varying over I x bar such that when I add this to the gradient and that then the whole sum is added to the normal cone to x at x bar, that new set must contain 0. So this Sx bar is now, I can keep it like this also, there is no problem, this is the optimality condition. But then a lot of insight is lost because you lose these multipliers which have a lot of importance in economics and optimization and engineering, and so it gives you a lot of insight into how optimization, how a minimization process goes on, so or maximization process goes on. So here what happens is that I've done a lot of printing mistakes, I admit. So you, 0 is element of grad fx bar plus this, so there exists some lambda is. So what, again I'll repeat, what does it mean? It means that there must be element here in, say, v in sx bar and say w in nxx bar, such that 0 is equal to grad fx bar plus v plus w. Of course v is all a v must be of the form lambda I grad gi x bar, so there must be some lambda i's such that summation lambda I grad gi x bar must be equal to that v, and we actually write it in an inclusion form, not in equality form, because we don't know anything about x, the structure, so we just keep it in the normal cone form. So then putting lambda I equal to 0 when I is not in ix bar, that is for which gi x bar is strictly less than 0, we'll get the conditions. So we will just write I equal to am here and then write the lambda I gi x bar equal to 0. Now let us look at the converse. That is, these two conditions which we call the Karush-Kuntakar condition, we will tell a bit more in detail. Is this condition also sufficient? That's the key thing that we want to know, that this condition, the Karush-Kuntakar condition for the convex programming problem CP1, is not just necessary but also sufficient. This is a very, very important thing to note, that this is a if and only if condition, and for constant optimization it is a huge thing, because once you solve the KKT system or the system of equations or inclusions, whatever equations finally, then, or inequalities, whatever you want to say, this system of equalities and inequalities, you, whatever you get is actually the solution of the problem, the global minimizer. So this is very important. So what we want to say, that if these two conditions, the conditions which are of the, which are the conclusions of theorem 8, which are necessary conditions. So what you get in theorem 8 is our necessary condition, grad here, the necessary conditions. But now we are trying to show that if there is an x bar feasible to CP1 and if there exists a lambda element of Rm plus such that this is true, then that this inequality holds and this complementary, this inclusion holds and this complementary slackness condition holds, then this x bar is actually a global minimizer of the problem CP1. So now if you look at, because f is convex and if gi's are convex and lambda is greater than equal to 0, f plus lambda 1 g1 plus lambda 2 g2 plus lambda and gn is a convex function. Thus for any x that you take in the feasible set of the problem CP1, then for that let us look at this, use the convexity of f plus summation lambda I gi. So if you look, so then if you take the gradient is again a linear operator. So you take the gradient of f plus summation I lambda I grad gi is same as this. Now again, you know, because this minus of grad fx plus in the bracket minus of grad fx, if I take a bracket, sorry, minus of in bracket grad fx plus summation I equal to 1 to m lambda I gi x bar is actually an element of the normal cone to x at x bar. That the condition 1 tells me. So minus of this condition into x minus x bar for any x in the feasible set is less than equal to 0, because x is also in capital X. Okay. Now what happens? So here, so negative is less than equal to 0. Negative of this inner product with x minus x bar is less than equal to 0, because from the first condition tells us that the negative of this full vector is in the normal cone. Okay. So this thing would become non-negative. So then what would happen? I will immediately have this condition that the difference of these two is greater than equal to 0. Now you know again lambda I gi x bar is equal to 0. So that is the complementary slackness condition. So you see how important it is. So this part will vanish. So I'll have fx minus fx bar is greater than equal to minus I equal to 1 to m lambda I gix. X being the feasible point, gix is less than equal to 0 and lambda is are all greater than equal to 0 because lambda is in Rm plus, right? So lambda is greater than equal to 0. So summation I equal to 1 to m lambda I gix bar is less than equal to 0 with, because here there is negative sign. This is a quantity which is greater than equal to 0, which means f of x is greater than equal to fx bar. And this is true for any feasible x that you choose for the problem CP1, proving that fx is bigger than equal to fx bar and x bar is the global minimizer of the problem CP1. So the two necessary conditions that appear in theorem 8 are also sufficient. So these conditions are the celebrated Karush-Kuntakar condition. In the original paper of 1951, which contained first the necessary conditions with the assumption that the problem data was continuously differentiable. They didn't bother about convexity while proving necessity. Here we have made huge use of convexity while proving even the necessary part. What they use something called Farkas lemma. I was very lucky enough to have a 30 minutes chat with in 2010 with the legendary Harold Kuhn, and he told me in details how they found the Karush-Kuntakar condition. It was a very interesting story. Okay, so I will not get into that here because I have not done. I am not going to do those issues here. So this their paper was published in 1951, and it was a paper which they gave in the Berkeley Symposium on Mathematical Statistics. And later on, this condition became so celebrated that Kuhn told me that once he was going to introduce Albert W. Tucker. Albert W. Tucker is, by the way, the PhD supervisor of John Nash. So Albert W. Tucker uh, was supposed to be introduced in a conference by Harold Kuhn, and Kuhn got up and said that I am Kuhn and he is Tucker, and that was enough. There was no need for any introduction. The condition has become so famous. So later on in 1980, Harold Kuhn was reading a book called Advanced Mathematical Economics by some Japanese author. I just forget his name, and there he discovered a note on Karush. Karush has done some work on these conditions, but for a very particular class of problems, the differential equations as side conditions, that is, differential equations as inequality, differential expressions as inequalities. And because Karush was in Chicago, possibly linked to the calculus of variation group of Magnus or Hestenes, and so Karush wrote a letter, nice letter. Sorry, Kuhn wrote a nice letter to Karush, telling them that because he already knew the thing for a particular case, his name should also be a part of these conditions. And he accepted, and then from that time onwards, it is known as the Karush-Kuntakar condition, and it goes by the smart name of KKT conditions. Does the KKT condition fail? That is the question. The KKT condition can fail if a very important condition, the Slater condition, fails. It doesn't mean that if the Slater condition is only sufficient for KKT to hold. It is not necessary that if for a convex programming problem a KKT condition holds, then the Slater condition has to hold. No, not really. See, please understand that what we are calling, you might be suddenly surprised that I am talking about convex optimization, that then convex programming. Please understand, by a convex optimization problem, I always mean minimization of a convex function over a convex set, or a maximization of a concave function over a convex set. This is a convex optimization problem. The convex set, how is it obtained, what is the structure exactly, I am not bothered. But when I'm talking about convex programming problem, I am bothered about the nature of C, because then I am looking at minimizing a convex function with respect to convex inequality or affine inequalities, right? And or I'm looking to maximize a concave function with respect to concave greater than equal to type inequalities and affine equalities. So uh, when your convex set is described by convex inequalities or concave inequalities, convex inequalities of the lesser than equal to type, concave inequalities of the greater than equal to type, and affine equalities, then only we will call such a convex optimization problem as a convex programming problem, because non-convex function inequality or equality representations can actually generate a convex set. We will not get into details, but a fair amount of research has come out in the recent years trying to show, starting from 2010 by a famous mathematician John Bernard Lazar in this area of optimization, that a convex set may not be always described by convex inequalities. There can be one or two non-convex inequalities among them. And then, under very mild modification, mild addition to the Slater condition, the Karush-Kuntakar condition is both necessary and sufficient. Because on the face of it, this is kind of a hidden convexity which is prevalent. So if a convex optimization problem means I take into account this broader scenario. Well, for convex programming problem, I stick to the case where my description is given by convex inequalities and affine inequalities, or concave inequality, greater than type inequalities and affine equalities. So here is a problem which will show you that if the Slater condition fails, your KKT condition may not hold. So you're minimizing the function fx over x equal, which is function fx of fx is a function of two variables, and you're minimizing the function fx, f of x1 x2 actually is equal to x1, and g1x is the circle of radius 1 which is centered at 0 1, and g2x is defined through the is a circular disk along with the circular boundary which is of radius 1 and centered at 0 minus 1. And the point these two sets intersect will give me the feasible set, and these 2 points intersect at the point 0 0. So the feasible set contains only one point, and that is the optimal value, which is 0 here. Now let us look at the gradient. If I calculate the gradient of this, it will be x1 0 because there is no x2 here. And if I calculate the gradient at 0 0 also, it will give you 1 0, it's constant. If I calculate the gradient of g1x, I'll get 2x1 and 2x2 minus 1, and if I put 0 0 there, so I'll get 0. If I put 2x2 minus 1, if I put 0 here, I'll get minus 2. So I'll get 0 minus 2, and grad g2 0 0, I'll get 0 2. Now if I add them, suppose I want, so what I have to do, I have to find lambda 1 and lambda 2 such that this grad f0 0 plus lambda 1 0 minus 2 plus lambda 2 0 2 equal to 0. Here capital X is equal to Rn, R2. So my n of R2 0 0 is 0. So my inclusion now becomes an equality as we had discussed earlier. This is what we had written here, this normal cone business here. Now, is this equality valid? Does this make sense? The answer is no, because if you want to add them, it will become 1 plus lambda 1 into 0 plus lambda into 0. So the first component of this new vector after summing is 1. The second component is minus 2 lambda plus 2 lambda to equal to 0. So first is you will get an absurd inequality like 1 equal to 0, and hence naturally that's absurd. So this equality cannot be true, and so the Karush-Kontoker condition doesn't hold. Now, of course, you can now will ask me the question, okay, if the Slater condition is just sufficient, can there be a situation where the Slater condition fails but the KKT condition actually holds? Proving that the Slater condition is truly not necessary, just a sufficient condition to guarantee that the Karush-Kontoker condition is holding. So this can be obtained by slightly tweaking this problem. Suppose instead of fx equal to x1, I take x1 square plus x2 square. Then also there will be only one minimum point, 0 0, and the functional value, the minimum value would be 0 0, the unconstant minimizer in fact for x1 square plus x2 square. Now in that case, if I want to run the KKT conditions, my grad of f at x1 x2 is 2x1 2x2, at 0 0 it is a vector 0 0. So what I'll get, the first equation would be 0 equal to 0, which is okay, meaning, And the second equation will give me minus 2 lambda 1 plus 2 lambda 2 equal to 0. If I put lambda 1 equal to lambda 2 equal to 1, then, or in fact lambda 1 equal to lambda 2, that's it, and not equal to 0, some non-zero quantity, say some 2, 3, 4, whatever. So in this case, I'll just showing that, okay, there exists a pair of lambda 1 and lambda 2 for which this inequality holds, which is lambda 1 equal to 1, lambda equal to 2, it will be a minus 2 plus 2, which will be 0. So this will equality would be satisfied when lambda 1 equal to lambda 2 equal to 1. So the Kuntaka condition is satisfied with the Kuntaka multiplies lambda 1 equal to 1 and lambda 2 equal to 1. Of course, there are many things, any lambda 1 equal to lambda 2 equal to non-zero. And hence the KKT condition holds in this case. So you are tweaking. So the Slater condition has failed because, as we have seen here, the Slater condition has failed because there is just only one point 0 0, and let us put 0 0 here. If I put 0 here, what happens? You will get 1. If I put 0 here, you'll get 1 minus 1, which is equal to 0. So active constant, if I put 0 here, you'll again get 1 minus 1, which is equal to 0, which is the active constant. Okay. Now I come to the max problem, which I mark as CP1A, because this problem is what economists would be very interested in, where f is a concave function. In many cases it is just a utility function, and subject to the fact that gix is greater than or equal to 0, where gi is a concave function and x is again the same, maybe a closed convex set, and we assume the functions to be differentiable. So the problem that I have asked you to show that, this should be gix greater than or equal to 0 is a convex set. That is, this feasible set of this problem is convex, the feasible set of CPA. Now the Slater condition for the CP1A is different. Which I would like to call it, when I would write my notes up, I will call this as the anti-Slater condition. Because by Slater condition, in the mind of us, the optimizers, it is ingrained that the Slater condition is written down for less than equal to type inequalities, and it is a xat for which gi xat is strictly less than 0. So, but when it comes to gix greater than equal to 0, we actually put it back into minus gix less than equal to 0, and we look for an x star such that minus gix star is strictly less than 0. So which means gix bar is strictly greater than 0. So this is what I'll call the anti-Slater condition, right? So when minus gi satisfies x, that system satisfies the gix less than equal to 0, that system satisfies the Slater condition. We will call that to be the anti-Slater condition, though here we are calling it Slater condition for CP1A. So what we do, we'll put this in the minimization problem, minimize minus fx subject to this. So what happens is that we have just changed the signs, that's all. And you know that minus of mean of minus fx is max of fx. So now we'll consider the situation where the Slater condition holds. So the anti-Slater condition or Slater condition CP1A holds. So for this problem, the normal Slater condition holds. And so just what we have learned there in the theorem 8, there exists lambda I greater than equal, mu I greater than equal to 0, such that my grad of minus fx here, f of x star. So the global maximizer of the problem CP1A is actually the global minimizer of this problem. So which we have already discussed in the last class. So now using theorem 8, which was the Karush-Kuntaka condition, we will get this minus of grad f1 x bar summation mu I minus of grad gi x bar plus nx x bar, and that too into lambda I into minus gi x bar. So this condition remains the same. So what do I have? I have grad fx star plus summation I equal to 1 to m mu I grad gi x bar minus element of nx x bar. Does it ring a bell? Does it ring a bell? Suppose the gi's were constants were not there, it would become grad fx star element of nx x star, the one which we had learned for maximizing the function over any arbitrary set C. That is what you will get. And if you look at the one for the minimization case, you have here minus of grad fx bar minus of this is element of an xx bar. If gi's are not there, it will be just nothing but minus grad of x bar element of xx bar, the thing that we had learned in the last class. Not last class, rather last to last class. Okay, so this is what we get. Okay, now if x is now open or x is Rn, then you will simply get this expression because this is nothing but 0. So which means this vector must also be equal to 0. Okay, which is the same Karush-Kuntaker condition which you get even for inequality constants of the less than equal to type with convexity. So for under concavity assumptions of on f and gi's and convexity assumption on the set x, capital X, you can show that this Kuntaker condition for maximizing the concave function over concave inequalities, greater than type inequalities under the same abstract contact x element of x, then the optimality when x is equal to Rn, say, then the optimality conditions for both the maximization case and the minimization case would look the same, though they are structurally very different problems. One deals with greater than type inequalities, another deals with lesser than type inequalities. Because greater than type inequalities is needed because the functions are now chosen to be concave. And for concavity, the greater than type inequalities actually furnish a convex set, not lesser than type inequalities. So now look at the situation where x equal to Rn plus. X equal to Rn plus is the situation where the economists are interested. Now we know how to write the normal cone of x equal to Rn plus. What is the n of Rn plus at x bar? That we have already done geometrically for n equal to R2, then extrapolated our ideas to n equal to Rn. What we now do is apply the theorem 7 to this particular set. Now Rn plus can be written like this, where each gjx is minus xj. gjx1, x2, x dot dot xn is minus xj. Now what you do is, once this is, you understand this, you want to now apply theorem 7 and see what happens. Then you easily know that a Slater condition holds, because obviously you can find an xj for which xj is all the xj's are strictly greater than 0. It is very simple, just take 1 1 1 1 1, that's it. All the xj's are 1. Now, which means by theorem 7 there is a v in Rn, any v in Rn plus would look like this. For any v, there must be a vector w in Rn plus, that is w1, w2, wn, which is greater than or equal to 0, such that v is equal to w1 into grad of g1x, which is minus x1, which is minus 1 into 0 0 0 transpose. w2 would be 0 minus 1 0 0 0, there's a mistake, and wn would be 0 0 0 minus 1. So it will be nothing but minus w1 minus w2 minus wn, which is minus of the w vector. Okay, so there exists some w in Rn, so v must be the negative of some element in Rn plus. So v must be somewhere an element in Rn minus Rn plus. V must belong to that. That is what we have seen from our discussion. For the R2 case, we made the things slightly more clear by taking the signs on x1 and x2 so that you know where it exactly lies. Here, that this will be more complicated because the combinatorics would be harder. Only thing to know that any element v will actually lie in minus Rn plus. That is what the theorem 7 tells us. So, when we consider that situation when x equal to Rn, we will finally reach a condition like this. Economists hardly write the things in terms of gradients. They always try to write them component wise in terms of the partial derivatives. So in terms of the partial derivatives, when you write that summation lambda I grad gi x bar, so you basically what you're doing, lambda 1 into grad g1 lambda 2 into grad g2. So if now lambda 1 into grad g1 means what? The lambda 1 is now first, if you take lambda 1, the lambda 1 first gets multiplied with uh, del g1 del g1 del x1 plus lambda 2 into del g1 uh, del g2 del x1, lambda 3 into del g3 del x3 plus lambda n into del jn del x1. So if the first line, and that is added with del f del x1. So that is what you are seeing here, that these xj's are changing. This lambda 1, lambda 2, they are the same, and these xj's are only changing, all evaluated at the point x star. Here what it says, now you will have this additional constant wj xj equal to 0, because that will come out of this computation of v. That v, of course, we have to really, when we compute v, we have to really bother at a point x bar, we have to bother about the active index constant. But if we take this additional complementary slackness condition wjxj equal to 0, so we do not really have to bother about this active index set. So here I've added the whole thing, so it is minus w, along with, I forgot to tell you before, that you must have this condition wjxj equal to 0. That came out even when we looked at it geometrically, from a pure geometrical point of view, without this algebraic relation of nf1 x bar equal to sx bar of theorem 7, which we are using in this particular setting for this particular case now. And then this is exactly the condition that you will have, and this proof we leave to the reader. You can understand this is coming from the computation of the normal cone of the GIs, and this is coming from the normal cone of Rn plus. So we leave this proof to the reader, and with this we would like to thank everyone to be a part of this course. I do not know how much you have been helped or how much you have understood, because the time was very, very short, because it takes a lot of time to prepare all this and then prepare your own self and then actually record it, and then suddenly while recording you realize that there are mistakes and try to correct them. So I would admit all the slips that I have made are my mistakes, and I very humbly apologize. I unfortunately, this COVID-19 situation has not left us to have uh, interactions. As a result, we have no much idea of how we have both grown, both the teacher and the student, while doing this subject. So now, because your exams are coming and we had to push through the course, a lot of things which I wanted to couldn't be done, but I think a lot of things had also been done. I hope you would agree with me. And though readers who are the viewers who are looking at these videos in the YouTube, for them I would say that please continue watching. I would fill up these gaps which are here, but they would be done in a much more interactive way. I'll try to actually write them through on a blackboard mode, and then try to explain you these things. Thank you very much. Thank you very much once again. All the best for the exams for the students. And the viewers, please, and the other viewers, please keep looking at my channel. You would find more and more videos on optimization being added up. Thank you very much.